I am Kumar Varoon Agrawal. I am an assistant professor at EPFL School of Basic Science, Institute of Chemical Sciences and Engineering. I am located in Satellite Campus in Sion. So in the picture, in my video, you could see a background. That's the Sion campus. The buildings are highlighted in gold. That's a new I-19 building where my labs are also located. Um, so that's me at EPFL. I run a lab which is developing new kinds of membranes for energy efficient separations. And when we say separations, we are dealing with molecular separations. And our approach to design these materials are based on material chemistry, right? And so what we are doing is we are looking at different set of molecules which is currently used in industry, but they are typically difficult to separate from each other. And the current conventional process are able to separate these, but at the expense of a large energy input. For example, for removing CO2 from nitrogen, right? So this is currently done at a large scale plants, capture plants connected to, for example, CO2 a power plant which emits CO2. And they're using this process by absorbing CO2 into a solvent. This process works very well, but the the purification of the solvent requires desorption of CO2 from the solvent and requires a lot of heat energy, right? So the goal in our lab is therefore to develop simpler technology which requires less energy for the same separation of the same set of molecules. And so our lab is now leading methods to develop a separation technology based on membranes. Now, what are membranes? Membranes are a separation process where we separate molecules based on their affinity towards the membrane, right? So across the membrane, there is a driving force. And for example, if the molecule is a smaller, you could take the example of a coffee filter, right? A coffee filter will allow the extract to go through, but not the particulates, right? So that's sort of a kitchen analogy, but generally, for example, CO2 is smaller than nitrogen. So we develop 2D membrane, two-dimensional membranes, where we can separate these molecules based on their differences of size, right? So if I want to discuss about the size of these two molecules, CO2 is 3.3 angstrom in size, nitrogen is 3.6 angstrom in size. So, and 1 angstrom is 10 order of magnitude smaller than 1 meter. So we are dealing with extremely small size, yet in material chemistry, we can still find space to differentiate these two molecules. For example, when we work with two-dimensional material, one of our favorite material is graphene, and there we can make pores or holes which can differentiate between these two molecules. To give a context of the capture penalty for CO2, the current commercial processes, as I mentioned briefly before, is based on solvent, and the solvent is amine. Amines have a strong interaction with CO2, and this is why the process works very well. But it's also one of the difficulties with this method, because amines are expensive and they have to be regenerated. But you have to spend quite a lot of heat energy, typically using steam, to regenerate the amines, right? And in this process, the net cost is the energy cost as well as the capital cost comes out to be quite high. The current state-of-the-art methods cost about anywhere between 50 to 110 US dollar per ton of CO2. And a large-scale plant is typically anywhere between 0.5 to 2 million tons of CO2 per year. So it's CO2 capture becomes quite an expensive process. Explain in the local context of Switzerland. In Switzerland, there is a carbon emission tax. That means the industries which release CO2 in the atmosphere, they have to pay a penalty. And this penalty used to be, I think a year or 2 years back, about $100 per ton, 100 CHF per ton of CO2. My industrial collaborators informed me that this is going to go up to 200 CHF per ton of CO2 in a year or two, right? So you see there is a steep constraint put it in on industry, a regulatory constraint, for a good reason, right? Because Switzerland Federal Council wants to cut the CO2 emission to zero by 2050. And so they have to apply these restrictions to motivate the industry to either find a renewable source or emission-free ways to run the industry or to capture CO2, right? So my projects are typically, several of my projects are working in this energy transition regime, where while we find a good way to switch to renewable energy and good way to completely avoid emissions, at least we can cut down the emissions till the time we are using fossil fuel. We are working on a separation technology which is primarily based on membrane-based separations. Now, membranes work by applying a concentration or a pressure difference across a thin film. The film is designed in a way that it allows only a component of a mixture to go through, either based on the interaction of the component with the membrane or how fast that component can go through the membrane. I can give you an example of a simple kitchen-based tool, which is coffee and coffee filter, right? So a coffee filter will allow the liquid coffee to go through, but the coffee beans or the debris would stay behind. So there, it's done based on a size difference, right? Because the liquid molecules are much smaller than the coffee beans and their debris. In fact, in our lab, we are developing a similar technology based on the size difference, but now we are talking about the size difference of molecules, right? So it gets very interesting in that sense, because molecules, I give you an example of separation of CO2 and nitrogen. They are quite small. The size of CO2 is 3.3 angstrom, size of nitrogen is 3.6 angstrom, right? An angstrom is 10 order of magnitude smaller than a meter, right? So human hair, for example, is typically anywhere between 30 to 100 micron thick. A micron is only 6th order of magnitude smaller than a meter, right? So you could see that these molecules are extremely small. The nice thing is we are working on the technology or materials which can allow us to separate these even such small molecules based on their size. I'll briefly explain to you how our top lead technology works. It's based on graphene. Graphene is an allotrope of carbon. It's made of a hexagonal packing of carbon atoms, but as a atom thick single layer, right? Now, what it does is there is carbon atoms packed closely, and it does not allow any gases to go through. There is not enough space for the gases to flow. Now, we use this as an advantage, and we just remove a few carbon atoms from the graphene lattice to make a hole, right? So we drill a hole in graphene. Because we are dealing with the size of an atom to manipulate and create a hole, we have the leverage to make extremely small holes, right? So this is where we can, for example, remove 10 carbon atom from graphene lattice. And what happens is when we remove 10 carbon atom from the graphene lattice, the hole that is created allows CO2 to go through, but it is small compared to the size of nitrogen. So the nitrogen molecule has a much higher difficulty to go through the hole. And this is the key reason why we can separate CO2 from nitrogen. By creating precise holes, we call them nanopores because they are a pore of the scale of a fraction of a nanometer. So this is why we are able to separate CO2 from nitrogen. Okay. Now, you asked a question about the indicator. The indicator that we use is how fast the molecule can flow through this membrane, right? We call this as a molecular flux or molecular flow rate divided by the area of the membrane, right? And the selectivity between the two molecules that we are trying to separate. For example, CO2 nitrogen selectivity could be anywhere between 20 and 30. What it means that if we put equal amount of CO2 and nitrogen on one side of the membrane, the other side of the membrane will have 20 to 30 times higher concentration of CO2 compared to nitrogen. Okay. Now, the other indicator that we use is a process simulation, right? So our process simulation says how much energy will it be required to separate these two molecules? This is important because we compare the energy difference or the energy that is required for a given separation, right? So I explained membranes, and in the context, I had explained the current commercial process based on a mean absorption, and a mean absorption had a cost of $50 to $110 per ton of CO2. According to our calculations, because we have a high flux from our membrane, because our membrane is only atom thick, we only require a small energy, much smaller energy. So our calculations tell us that we require an energy of 25 to 30 CHF per ton of CO2, right? So it's about half to a quarter of the energy of the cost compared to what is needed for commercial technology. So we are quite excited about this, and we are trying to develop the membrane for future application. We are quite excited with this technology, mainly because we are going for a pilot plant demonstration. We are already funded by Canton of Valais. As I mentioned, we are now having talks with GAZNAT to do a pilot plant demonstration in Aigle. If this works out, the plan is that within 3 to 5 years from now, we will demonstrate the technology to capture 10 kilograms of CO2 per day, right? And if that works out, there is going to be a startup on this technology making practical scale membranes, at least for the small scale operation for CO2 nitrogen separation. And based on that, we would be scaling it further for a medium to large scale application. So this is the context of CO2 capture. And there will be a pipeline of activities for other gas separation. Now that we have moved ahead in technology readiness level for CO2 separation, we are starting some fundamental research on other gas separation. For example, I mentioned before hydrocarbon separations. The other interesting separation that we are working on is oxygen-nitrogen separation. And it has a large implication as well, because it could be used in hospitals, where we can separate oxygen from nitrogen at source. We take air, which has 20% oxygen, and we can purify oxygen to enough for using in oxygenators. The other separation that we think we would be able to do in future would be separating small ions from each other. For example, lithium ion from calcium and magnesium ion. That we think could help the battery industry, where currently ions are separated from each other. For example, lithium ion is harvested from brines in Chile by quite expensive extraction process. So these are the things that we will start to look at more on the fundamental basis in terms of the impact of these membranes on various separations. And as I said before, CO2 nitrogen separation, carbon capture, we expect that technology will be in the market for small to medium scale processes.